Hello, Chem1A. This is Chapter 10, Lecture Video 2, and we're going to be talking about how to draw Lewis structures. This is going to be a rather long video due to the nature of how much we have to talk about, so get ready. I'm sorry. So when we have two atoms bonded together in a covalent bond, we usually draw the electrons that are being shared in the covalent bond as a line or a pair of dots. But primarily this is going to be a line in our case. The pair of dots is kind of the older way of doing this. Now if we look at the Lewis structure of a hydrogen, we're going to look at the H2 molecule in this case as pretty much the simplest molecule, period, because it only involves 2 electrons total. An H atom has a Lewis symbol of this, right? And an H2 molecule is kind of like putting 2 of those H Lewis symbols next to each other. The electrons here are what are being shared. And we draw this pair as a line to indicate, hey, there is a covalent bond, specifically a single bond present between the 2 hydrogen atoms holding this molecule together. Now, this would be pretty much the simplest structure we could draw, but is known as a Lewis structure or Lewis electron dot structure. We're going to do a little bit more of a complicated example next.
Let's do something a little bit more complex. Sometimes we have electrons that are still present in our Lewis structure but are not actually part of a chemical bond. We call these lone pairs, often symbolized by an LP. So we look at H and in this case F. F's Lewis symbol looks like this. H's Lewis symbol looks like this. When they come together, we get this. These are the 2 electrons in the covalent bond that are being shared, right? So we have these 2 electrons being shared. The rest of these are what we call lone pairs. They're not actually being shared. They're just kind of hanging out on the fluorine atom. Now, one of the things that we're going to see here is that, again, we don't keep that guy like this. We're going to make that a line. So the correct Lewis structure for this guy would actually look something like this guy, right? Where we have, this is our bond, it contains 2 electrons, and then each of these is also needing to stay as lone pairs around the fluorine. Now, if we count fluorine's electrons, there are 2 here, 2, 2, 2. There are 8 valence electrons around this fluorine, which is the whole point of the bond, and we'll talk more about that as we go. But this is the Lewis structure of HF. So let's continue, and we'll go through some more in-depth rules on how to actually draw Lewis structures. Now this is a single bond, and we'll show how to do double bonds and all that. Really, it's just 2 lines for a double bond and 3 lines. So writing Lewis structures has some guidelines. The first thing we want to do is we want to calculate the total number of valence electrons in the molecule. After that, or while we're doing that, we need to keep track of ions. If we have an anion, something with a negative charge, we add 1 electron to the total of the valence electrons for each negative charge. The opposite is true of cations. So if we have a positively charged thing, we're going to subtract 1 electron for each positive charge from the total valence electrons. Then we're going to build what we call a skeleton structure. And a skeleton structure has an atom in the center, kind of like X right here, with everything else attached to it. All right, so each of these lines goes to what we call a terminal atom. Now, we got to figure out what this guy is in the structure. The atom that's the central atom is usually the one with the lowest electron affinity. And electron affinity is one of the trends we learned about in Chapter 8. Hydrogen and fluorine, you should know, are never central atoms. Not ever. So once we have our central atom chosen, we're going to attach each one of the terminal atoms to the central atom with a single bond, 1 pair of electrons. And that's going to build what we call the skeleton structure of our molecule. or our Lewis structure. And I'll go through all this in depth on the next slide using examples. Once we have our skeleton structure, we need to complete the octets, i.e. make sure each atom around the central atom, not the central atom itself, but the terminal atoms, all have octets, i.e. 8 valence electrons surrounding them. And we can do this by adding lone pairs to each terminal atom until they have 8 valence electrons. At this point, we need to count, see how many total valence electrons we have left, because the max number of electrons and the exact amount of electrons we should have in our structure at the end is equal to the total we calculated here at the beginning. And so we subtract, we figure out how much we used, and we figure out how many we have left. And if we have left over, then we got to keep adding them. If we are out of electrons or we use too many, we got to erase and figure out what to do. If we have extras, we're going to place any remaining electrons on the central atom as lone pairs. If the central atom has fewer than an octet, even though we added all we could here in this step, then we may need to make double or triple bonds as necessary, pulling electrons from the terminals that we had placed as lone pairs into double or triple bonds as needed. One thing you should know is that hydrogen atoms and actually fluorine will never have not lone pairs, will never have multiple bonds. So hydrogen will never have lone pairs. Fluorine will, but fluorine will not have multiple bonds. Ever. So let's do some practice problems. So again, double bonds are just going to look like 2 lines here. Kind of, you can see it here. A single bond, like we've seen, has just been 1 line. A triple bond is 3 lines. Each one of these lines is 2 valence electrons. So these two are sharing 6 total valence electrons just in this bond. Now it's hard to tell from this from the picture, but as we get to a double bond versus a single bond versus a triple bond, the bond length actually gets smaller as we increase the number of bonds. So a single bond is the longest of the 3. A double bond is shorter than a single bond but longer than a triple bond, and a triple bond is the shortest type of bond. So if we do some example problems here, the first thing we need to do is we need to calculate how many valence electrons. I know carbon has 4 valence electrons and hydrogen has 1 valence electron. I have 4 hydrogens. Does that make sense? So from these two numbers we can get our total, right? So for instance, carbon plus 4 H's, right? Or in other words, 4 valence electrons plus 1 valence electron times 4 gives me a total of 8 valence electrons that I can put on this structure for CH4. And I'm just going to erase all this calculations so that I can actually have some room here. But you get the idea. We have a total of 8 valence electrons that we can put on this Lewis structure. So the next bit, once we know, hey, I have 8 valence electrons here, is to figure out what the central atom is. Now, this is kind of a give me one because hydrogen cannot be a central atom, as we learned. So carbon has to be the central atom. So the next thing I'm going to do is I'm going to attach each of my hydrogens to the central atom using a single bond. And if we look at this, here's 2 electrons, here's 2 electrons, here's 2 electrons, here's 2 electrons. That's a total of 8 valence electrons, and we are out of valence electrons because our structure can only have 8 of them. And this is actually the correct Lewis structure for CH4. Let's look at NH3. All right, so nitrogen has 5 valence electrons, and each hydrogen, like we just talked about a second ago, has 1. We got to multiply by 3. This guy also has 8 valence electrons. Nitrogen is our central atom, again, hydrogens cannot be central atoms, so we attach each of our hydrogens to the nitrogen, and we go, great, cool. I have used 2, 4, 6 valence electrons in drawing this structure, but this time I haven't used all of them. I still have 2 left. And if you remember our rules from the previous slide, after we write our skeleton structure like we just did, we need to put lone pairs on the terminal atoms to make sure they fulfill the octet rule. Now, with hydrogen, it's a little bit tricky because hydrogen actually doesn't need to have 8 valence electrons around it. It should only have 2. So all of our hydrogen atoms in this structure are good. So we move on to the next thing. Nitrogen does need to have 8 valence electrons, and currently it only has 6 around it. So the next step is any remaining electrons we throw onto the central atom as a lone pair. Here's my lone pair. Now everything's good, and this is the correct Lewis structure for NH3. Let's look at CO2. So we got to count our valence electrons again. Carbon has 4 valence electrons, oxygen has 6 valence electrons, and we have 2 oxygens. So this gives me a total of 16 valence electrons. We got to figure out what our central atom is. It's the one with the lowest electron affinity. That would be carbon. So carbon, and then I'm going to attach to my carbon each oxygen with a single bond. So I've used up 4, because 2, 4, of my total valence electrons of 16. So I still have 12 more to go. So let's put lone pairs on the terminal atoms until they have octets, which now they do. At this point, we go, okay, how many electrons do we have left? None. We don't have any more electrons we can put on the structure. We've used all 16. See, 2, 4, 6, 8, 10, 12, 14, 16, right? So used up all the electrons. Now let's look at the structure and go, cool. Well, if we had any remaining, we put it on the central atom. We don't. Can't put it on the central atom. Does everything have an octet? Well, both oxygens have octets, but carbon only has 4 electrons around it, and that's not enough. So what we need to do is we need to erase some of our lone pairs. It doesn't matter which ones you erase on this oxygen, but I'm going to move them into a double bond. If we look at this oxygen, now there's 2 plus 2. That's a total of 4 electrons right there. And we still have the other 4 around oxygen from the lone pairs. So oxygen still has an octet. And now carbon has a total of 6 electrons around it. 2 here and 4 there. So we're closer. Generally, we want to try to keep symmetrical as much as possible. So I'm going to erase another lone pair, but this time from the other oxygen, and I'm going to move it into another double bond. And now everything has an octet, and this is the correct Lewis structure for CO2. If we look at SiO2, it's going to be very similar. We still have 16 valence electrons if you calculate it. Si is going to be our central atom. We're going to connect the oxygens to each one, do our lone pairs, and we're out of electrons. And so kind of the same thing, we're going to erase some lone pairs, put another line there in between the oxygen and the silicon. Again, it doesn't matter which lone pair you erase, pick one and make your double bonds, and this would be an acceptable Lewis structure for SiO2. So I'm going to erase some of this to give me some more room. Let's look at carbonate. So if we want to draw the Lewis structure for carbonate, we need to calculate valence electrons. We have 4 from carbon plus 6 valence electrons from each oxygen times 3 though. So this gives us a total of 22 valence electrons. But wait, we have a -2 charge, and according to our rules, for each negative charge, we need to add another valence electron. So because we have a -2 charge, we need to add 2 more valence electrons, giving us a total of 24 valence electrons. Carbon is my central atom because it has a lower electron affinity than oxygen. And so I'm going to attach to each one of my carbon, to each oxygen to the carbon using a single bond. And so at this point, okay, so next we have to add our lone pairs to the oxygens, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's not letting me draw there for some reason. 14, 15, 16, 17, 18. Awesome. So I've used 18 around the lone pairs and another 6 around my single bonds. So I've used all 24 valence electrons. But carbon still does not have an octet. It only has 6 electrons around it. So again, pick any one of these oxygens, doesn't matter. Erase a lone pair and move it into a double bond. Now everything has an octet. And this is very close to complete, but because this is an ion, we need to put brackets around our structure and put a -2 charge on the outside to show, hey, this guy has a -2 charge overall. And so that's how we do carbonate's Lewis structure. All right, so I think I actually do have a couple more, maybe one more to show. Let me just get some room here. So if we look at IBr2 plus, I think this is the last one. Each of these, I has 7 valence electrons, whereas Br also has 7 valence electrons. So I have to go, okay, 7 valence electrons from I plus 7 valence electrons times 2 Brs from Br2 plus, well, actually minus, 1 valence electron, because we have this positive charge, and when we have a positive charge, we subtract 1 from it. So this gives us a total of 20 valence electrons on IBr 2 plus. All right, so there we go. Awesome. Well, now we got to figure out the central atom. I has the lower electron affinity, so we write I, and then we put Br, and we attach each Br with a single bond. Now, at the end of the day, we're almost done here. We need to put lone pairs around the terminal atoms. So there's all my lone pairs. And if we look at how many we've done, we have had 2, 4, 6, 8, 10, 12, and then this is 14 and 16. I don't have 18 valence or 20 valence electrons on here. I still have 4 more to go, and they have to go on the central atom. And everything has an octet now. We need to put brackets again and the positive sign here to finish the structure.